welcome back. So we have been discussing the topic of BJT. We have covered quite a few subtopics within BJT. We have discussed the current transport, the various factors like gain, current transport, the base transport factor, current gain, and so on. If you remember in the last class, we also had discussed about things like Gammel number and early voltage, which are very important in a BJT, right? We have very thoroughly understood the different components of base current, emitter, collector current, how actually a BJT works, and what is it that makes a BJT amplify the signal. Okay, it's a current input device, and we have more or less covered most of the fundamental things that are required to understand in a BJT. So what is remaining now in BJT is delay, right? There is something called delay, or how fast a BJT can operate. Okay, you want to operate a BJT very fast in RF transistor, as an RF transistor for example. So how fast can it operate? That is something that is remaining. So in today's lecture we will definitely cover delay. Okay, what is the speed at which a transistor can operate, a BJT can operate? That is something we will do it from the device point of view. But before that we will continue slightly from the last slide where we had left in the last class. Okay, so we will come to the whiteboard. If you recall, in the last class I had told you about the early voltage and early effect, and I told you that in general for a BJT to work well, or to BJT to give you higher gain, the emitter doping should be very high compared to the base doping. If you remember, the emitter doping should be, this is emitter doping NDE and this is base doping NAB. So the emitter doping should be much higher than the base doping, in order for only then the gain beta will be high, right, and you will get gain in the device. But I told you in the last class, in the last slide, that the emitter cannot be arbitrarily doped very high. Okay, you cannot dope the emitter arbitrarily very high, because if you recall from one of the earlier lectures, if you dope very high, if you dope a semiconductor very high, then what will happen is that your band gap will shrink or will reduce. Your band gap will reduce. Okay, if you dope very high, for example, if you take a silicon BJT and your emitter is doped very high, say 5 into 10 to the power 19 per centimeter cube, that is an extremely high doping for silicon. So then what will happen is that your band gap will shrink from 1.1 electron volt to a lower value, maybe 0.9 electron volt or even lower maybe. What will happen is that when your band gap shrinks, your intrinsic carrier concentration Ni will increase, because Ni depends exponentially on the inverse of band gap. So if your band gap becomes lower, your intrinsic carrier concentration Ni will increase exponentially, and so this term Ni that gets cancelled out in the equations will not get cancelled out now. So what will happen eventually is that your expression for beta that you have an expression for beta, if you recall, that expression will now get reduced by a factor of e to the power minus delta Eg by kT, where delta Eg is the band gap reduction. So in this case, if the band gap reduces from 1.1 eV to 0.9 EV in the emitter, only in the emitter, because you are doping it high, then the reduction in band gap is 0.2 EV. So this term will be e to the power minus 0.2 at room temperature 0.026 will be like e to the power minus 9. So whatever you had beta, suppose you had a beta of 100, if you dope it extremely high, will get reduced by e to the power minus 9, and e to the power minus 9 is a very large number. So for example, e square, you can say e square is almost 10, so e to the power minus 9 will be like 10 to the power 5 or so. So this beta will be much lower than 1, so your gain has gone for a toss. So what it means is that you cannot arbitrarily dope the emitter high, because band gap narrowing effect will it will lead to a reduction in the gain. So essentially what I am trying to say is that initially, if you plot the gain beta versus if you plot the gain beta versus the emitter doping and doping in the emitter, then your higher emitter doping, your beta increases. But at one point when the emitter's band gap will start to shrink, then this gain will come down, right? So you cannot dope, this is doping, right? So this may be 10 to the power 15, 10 to the power 17, 10 to the power 19, and so on, 10 to the power 20. It cannot, it will not be even 10 to the power 20, at 10 to the power 18 or so it will probably start to come down. So your gain will come down, so you cannot arbitrarily do that very high, right? So these are the things that we have studied. What we have studied? We have studied current, the various current equations, and the current transport in a BJT, the base component of the current, emitter injected current, base inducted current, recombination current, and so on. We have studied things like the current, the base transport factor, the emitter injection efficiency, the beta, the gain, the current transfer ratio, alpha, these things we have studied. We have studied the Gammel number, right? We have studied the Gammel number, and the early voltage, how important they are in a device. We have studied this, like emitter shrinking effect, emitter band gap shrinking effect, right. So, we have studied most of the things that are required to understand the working of a BJT, right. So, the next thing that now we have to do is to study the delay. Okay. So, most of the things are clear, and of course, if in case of any doubts in any of this, either of especially the current equations can be little bit confusing if you have because you have so many different area types of current there. So, if you have any confusion, you are always free to email me, or we can discuss offline definitely, right. And you know how a BJT amplifies the signal, that we also have discussed. Now, what remains is basically delay. So, we will now start and finish up delay. So, what does delay mean? Okay, what does delay mean? Delay essentially is in a way related to how fast the transistor can operate. So, for example, if you talk about a BJT, this is your emitter which is highly doped, this is your base, and this is your collector, and emitter has a very small depletion region here, right, and the base collector has a wide depletion region here, if you recall, right. I call this WBC, the base collector depletion width. This is very narrow, this is base emitter depletion width, and of course your the neutral base width has become now WBN. This WBN is the neutral base width, remember, that is equal to the original base width minus the depletion that you subtract. This depletion, the depletion towards the base side and depletion towards the base side, this if you subtract from the original base, you get the neutral base width. Okay. The neutral base width essentially is the width of the base after you subtract the depletion that is extending towards the base from both emitter side and collector side. Okay. You see this blue, this is the metallurgical width of the base, this point to this point, that is the metallurgical width of the base, and that is WB. You subtract this part and this part, you get WBN. Okay. This is WBN. Alright. So, essentially when an electron moves from emitter to collector, what is the total time it takes? That is called tau, and that is the delay. What is the time that electrons take to reach the collector from emitter? Okay, that is called the tau, the total time, that is called delay. If you make this delay the time shorter, your frequency of operation can be faster. Your transistor will work faster if the delay is smaller. And there is something called a cutoff frequency, or FT. FT is defined as the frequency at which the current gain is 1, which means your output current by input current. Output current is collector current, input current is base current. That ratio becomes 1, which means your gain is 1. Above this, your gain will be less than 1, there will be no gain. Okay. So, gain has to happen only at a frequency less than FT. So, if I am plotting frequency here, and this I am plotting the log of gain here, which is IC by IB, then this will fall off at point, and in log scale it is 0, which is 1, log of 1 is 0. So, this point is called FT, it is called current gain cutoff frequency, and beyond this your the gain will be less than 1, on log scale it will be negative. So, to get some gain you have to operate in this regime, right. Basically this is the current gain cutoff frequency FT, and FT is basically given by 1 by 2 pi tau, this tau. So, a frequency will be faster, and this is in gigahertz or hertz, it will be faster when your tau is smaller. So, an electron when it goes from the emitter side to the collector side, it will encounter many delays. So, those delays will add up and give you the total delay. So, what are the delays that we should remember? So, remember when an electron moves, it will also have to go through capacitors, and there will always be capacitive charging and discharging of capacitors which will add to delay. For example, let me draw a good picture here. So, this is again I am drawing the emitter base collector. Emitter will have a small depletion region here, and collector will have a large depletion region here. Okay. So, this capacitance, this is a depletion region in a forward bias emitter base junction. This capacitance will store some charge, and that will be delta QBE, base emitter charge. Similarly, this will store some charge which will be delta QBC. That means every time you are putting a small signal, you are going to modulate this charge, which is delta QBC, the charge that is stored here. Of course, you are operating the base emitter in a forward bias, so you will be injecting carriers from electron from the emitter to the base. So, they will decay here like that, the base electrons will in the base will decay like that, which almost comes to 0 here, not exactly 0, but every time you change the small signal, essentially if you are changing the input by a small signal like an AC signal, what is the charge that you are actually modulating? Okay. So, every time you are changing the input signal by a small amount in a sinusoidal way, you are going to change the charge that you are injecting into the base also by a small amount here. At this point, of course, it has to come to 0. Okay. by a small amount that you are changing the charge here, and that is your delta QF, that is the charge stored in the base. Because the minority carrier electrons are injected to base, the charge stored in the base also will be modulated by a small signal, okay, that we refer to as delta QF. So it's interesting to note that there are many delays that are associated now. So the delay, the total delay will be made up of, one thing is that you have to charge and discharge this capacitor. So there will be delay associated with the emitter base capacitor, which is this, right. Then the electrons will have to travel through the base. There will be two types of delay there. I'll call them the base delay only. I'll discuss the later. So this is the emitter delay, that is the emitter base capacitor charging. As the electrons travel through base, there are two types of delays that will come, that will be clubbed under base delay, and then there is a collector delay, because there is a charging and discharging of the capacitor, and also the electrons have to travel through this distance. So there is also transit delay as they move across. Also there is a charging discharging delay here. So both of them are clubbed in here. So the base has two components of delay, right, and the emitter also has two, the collector also has two components of delay. One is the transit delay, because the electrons have to travel through this WBC, the base collector depletion, electrons have to physically travel across that. So that is the transit delay. One is the base collector capacitance, the capacitance charging delay, because the base collector will have a capacitance, and that this capacitance will have to charge and discharge. So that charging and discharging delay will be there. There will be transit delay that crosses. Now base has two components. One is called transit delay in the base. Transit delay is the fact that electrons have to travel from across the base. Electrons have to travel across the base physically. So there is a time that it will take to cross the base, that's called transit delay, right. And remember, the transit delay will be associated only with WBN, the neutral base width that we are talking about, okay. And then there is another type of base delay, and that is the total charge stored in the base. You see there is a charge that is stored in the base, right. This is the charge that you are modulating, this is the base. There is a charge that is stored in the base, right. There is a charge stored in the base, divided by the current that is clearing it. There is a current, that is the current that is flowing out, right. There is very much a current that is flowing out. That current is your output current, right. The current that is flowing out is clearing out the charge that is stored in the base, okay. So the base has some charge, and that charge is being cleared out by the collector current. So that charge clearing out also will add to another delay, okay. It's also another adding to another delay. So all of this have to be added up to eventually give out the total delay. So now if you look into each of these delays, right. So what about the base emitter delay? What about the base emitter delay, right. So let me see. You have a small base emitter forward bias depletion region. This is a very tiny depletion region, but essentially the delay with the base emitter junction will be given by whatever the capacitance associated with that is there, which is CBE times your resistance, that is the RC delay, if you recall, okay. And what is the resistance that you associate with that? The resistance you associate with that essentially is your the resistance, you can say, is actually with respect to the, this is emitter, this is base. So if you connect this in the positive bias and a forward bias, the change in the base emitter voltage with respect to the current that is going out, which is IE, but IE is almost equal to IC, so I can say this is IC, right. So this is essentially we can say resistor, or the inverse of this will be called the transconductance in a way. The transconductance, that is the output current with respect to the input voltage, how much is it changing, right. So in a way you can say that the output current is this current. How much is the output current changing with the input voltage? Input voltage is the voltage here, so tau VBE. So this is called transconductance, and it gives you essentially how much is the tunability of the transistor, like how much is the output current changing with respect to the input voltage. And if you recall, IC actually is given by e to the power q VBE by kT minus 1 with some term like q dn by ln and all these things. So if you do that, if you do this, the derivation, you will find out that Gm actually is, which is 1 by R, Re I can say, is actually given by q Jc by k So essentially your GM is dependent on the current that you are doing, JC, okay, because it's an exponential function. So then if I put the delay tau BBE, it will be RC delay, and this will be given by R will be given by the inverse of this, which is KT by Q, the output current, into C, capacitor is the capacitance here, which is epsilon naught epsilon S into area. Of course, if I normalize with respect to area, then it doesn't matter, divided by the width, base emitter depletion width. The base emitter depletion width is very narrow, okay, that is one thing. And you see this delay, this is the total emitter based charging delay, okay, this is the emitter based charging delay, this is the emitter base charging delay, and this delay is inversely proportional to 1 by JC, if you recall. What it means is that if you increase the current density, if you increase the current density of the output current somehow by either biasing it much at higher voltage, in some way if you increase the output current density, then your delay also will come down. And this is a unique situation, because in conventional MOSFETs you will not get this kind of a behavior. Only in BJT you get this behavior that with increasing output current your delay can come down. It is a very beautiful result actually, but this is basically your emitter delay, and the emitter delay could be significant or may not be also significant in some cases. Next is the base delay. There are two components of base delay I keep telling you about, right. So if I look again at the transistor, if I focus on the base, this is an emitter base depletion region, this is the base collector depletion region. What remains here, what remains here is the neutral base width, okay. So what is the time that you require to supply additional charge? What is the time required to supply additional charge delta QF, okay, to this quasi neutral base region? You are injecting carriers, they are decaying and they are coming to almost 0 here. So this is a charge that you are modulating when you apply a small signal. So what is the time required to essentially supply the additional charge that to the quasi neutral base region, okay. This charge is almost 0 but not exactly 0, right. So you know so essentially for any change that you have here, so if you look into this condition again, if I am drawing this condition here, so suppose I have a carrier profile that is decreasing like that. If I am changing it by a small amount delta n at 0 here, then it is coming like that. This is the charge that you are modulating essentially, which I am calling as delta QF, right. It is the charge, okay. But here it will not come exactly to 0, but it will come to some value. It will not be exactly 0. The reason is there is a velocity saturation. So it will not be exactly 0, but there will be some small value, okay. There will be some small value over which it will modulate, and that modulated value will be delta n at this point, which is WBN, okay. What I am trying to say is that because of a finite velocity saturation, it will not, this point will not become 0, there will be some spread there. So there is a spread here, you are doing a small signal modulation, you are going to change some charge there. So there will be a spread here and there will be a spread here, okay. So essentially your there is a charge that, so basically what is the time that you require to charge and discharge the the base, there will be base charge and there will be current that is going out. So how fast is this current carrying out this charge, okay. That component is very important in the base delay, and that component is basically given by WBN square, okay. This is the WBN square by 2dn, this is the diffusion coefficient, okay. So this component WBN square by 2dn, it tells you essentially the charge that is stored in the base divided by the current that is clearing it out, that ratio, okay, how fast you are clearing out the charge stored in the base. This is what it tells. There is another base component which is the transit. So the base electrons are moving across the base, they are going from this point to that point, so they are covering the base. That is basically the transit time, that is this distance, which is WBN, divided by the velocity with which they move. The maximum velocity they can move is Vsat. So this is the total base delay, this is the total base delay, okay. That is the total base delay, okay. So basically you will have a small change in the signal will give you a small perturbation in the charge that you are storing in the base, and there will be a small spread here also, because it's a finite velocity, there is not an infinite velocity. So the collector side, the carrier density of the collector side also rises, there is a small spread here, and you need to supply an additional charge that will essentially make sure that there is a spread here and there is a spread here. How to clear the charge is basically, this is the delay associated with that, and your the way you calculate this essentially is the total charge stored in the base, which is 0 to WBN, the total charge stored in the base, the minority charge, okay, divided by the current that is clearing out JC. You put the expression for JC, the current expression, you will get this expression actually, okay. And this is basically the transit time. If you have a base thickness of this 100 nanometer and the velocity of saturation is say 10 to the power 7, okay, 10 to the power 7 per centimeter per second, then how fast are the electrons moving across that is the base delay. This is given by, say in this case, 100 nanometer divided by 10 to the power 7 centimeter per second. That will give you, this ratio will give you in nanosecond or picosecond, whatever, the delay associated with the electrons moving across the base. So we now know this base component. Final delay is the collector delay, okay. You see this collector will charge and discharge, so there will be two delays associated with that. So I keep telling you that one is that if I only draw the base collector, for example, I only draw the base collector, this is base, this is collector, there will be small depletion of the base because the base is higher compared to the collector. This is the collector, this is the base collector depletion region. So this entire thickness is WBC. So the capacitance associated with base collector is epsilon S, epsilon naught by WBC. This is normalized capacitance, so this is farad per centimeter square, right. So this is your base collector capacitance, and that base collector capacitance has to be multiplied by all the parasitic resistances associated with collector. I will call it RC. That will give you the base collector delay, base collector charging and discharging delay, okay. This is the base charging delay that you will have, and typically this will consist of all the parasitic resistances that you might have, RE plus RC for example, okay. This will be given in the question. This is the base collector capacitance which is given by this expression. So this term, this entire term gives you the charging and discharging delay of the base collector capacitance, okay. And finally you have electron that will actually cross across this and will be collected in the collector. So the electron will take some time to physically cross this depletion region. If this depletion region is WBC and if the electron moves at a velocity of V set, then this delay should be ideally WBC, this distance divided by the velocity with which they are moving, which is V set, except that there will be a factor of 2 here. Do you know why? Because this part is depleted. This is a depleted part, not unlike the base. This is unlike the base, this is a depleted part. And whenever there is a depletion part, that means there is no free carriers there. Whenever there is a depleted part, suppose this is your depleted part, okay, which means there is no carrier concentration almost there, an electron is moving through a depleted part, then the transport is called space charge transport. The transport is called space charge transport. The space charge transport is a type of transport just like you have drift and diffusion that we have learned in the course, if you remember. Similarly, space charge transport is a specific type of transport, not exactly drift diffusion, where the electric field is dragged by the carriers that are moving in a depleted film. So the electric field within this is defined by essentially the carriers that are moving across the film, and the background carrier is very low, so it's almost depleted. So in like organic semiconductor or insulators for example, which have very low background concentration like a dielectric, the transport typically is space charge transport, because the carriers that you are injecting will define the field inside. So in space charge transport, it so happens that the time taken will not be the ratio of WBC by the velocity, the distance by velocity, but it will be distance by 2 times the velocity or half the distance by velocity, okay. So now we know the various terms that are associated with the delay. So let us write them down. The total delay is given by the base emitter delay, which is your base emitter delay, is responsible for the charging and discharging of the base emitter capacitor that we had just talked about. So the base emitter delay will be KT by Q IC into epsilon S epsilon naught by WBE. Then there are two components of base delay. One is the base transit time by velocity saturation, that is the time taken to cross the base. One is the charging and the clearing up the charge stored in the base. This Dn is the diffusion coefficient, WBN is the neutral base width. So this gives you the time required to clear up the charge in the base Then there is a base collector capacitance delay epsilon naught epsilon s by WBC. This is the base collector capacitance delay. Finally, there is a transit delay across the base collector depletion region, that is given by WBC by 2V set. Now, if you recall here, this term will become small. You want this to be small so that the transistor becomes faster. So, this term will be small if your base width the base collector depletion width becomes large, but this part time will become small if the base collector depletion width WBC becomes small. So, here you have to increase WBC, here you have to reduce WBC. So, there is always an optimized WBC, which is the optimized base collector depletion width across which you will be minimizing this sum. You will be minimizing this sum. Okay. Similarly, you see that base width, the neutral base width has to be small. The thinner the base is, the faster the devices will be, because the delay will come down. And this delay does not matter in many cases, but it can also matter by increasing the JC very large, you can reduce the delay substantially, in which case only these delays and these delays will matter. These delays will basically come down if your base is thin, so that WBN is small. This delay will come down with an optimized approach, because it is like k by x plus x by m, this kind of an expression. So, you have to minimize the expression, and the minimization will happen at x equal to like k m, I guess, right, square root of k m. So, there will be a point where you can do that. So, this is the total delay. There could be numericals, that will ask you to solve these delays and what different kinds of delays will affect the devices. You have to understand that there is a trade off in terms of the base collector capacitance, and also this WBN is the neutral base width. So, you have to subtract out the depletion of from the towards the base from the metallurgical base width, right. So, this is all about delay, and you can see that state of the art BJT. BJT actually has many drawbacks. So, it has an advanced version called HBT. To understand HBT, we have to understand heterojunctions and compound semiconductor, but HBT is a heterojunction bipolar transistor, which is very similar to BJT, except that you use materials of different materials actually for the emitter and base. But in a record, HBT is an advanced version of BJT. The cutoff frequency FT greater than 700 gigahertz have been the record, not in silicon, but I guess in indium arsenide system. Okay, silicon cannot have that kind of FT. Okay, so there are devices that can actually almost go to 700 or even more than that gigahertz, but again you do not operate the device at 700 gigahertz. It means that the maximum frequency you can go is 700 gigahertz. Okay, so that brings us to the conclusion of our ending of this lecture, and with that we basically finish up the BJT. So, the topic of BJT with different the important parts that we had to discuss are now over. So, what is remaining now is that we will visit BJT very briefly when we discuss about compound semiconductor and heterojunction, because when you have compound semiconductor and heterojunction, then you can overcome some of the problems of BJT like emitter band gap shrinking and a low gain. Okay. So, that enables you to get high gain despite emitter doping being very high. So, those things we will just touch base when we talk about heterojunctions and compound semiconductors. Okay. But as of now, for classical silicon based BJT, whatever we have covered till now is more or less sufficient to understand how the BJTs work. There are more advanced things like Kirk effect, which is a high injection effect that we have excluded from the syllabus. That is a nonlinear effect sort of thing, but you are most welcome to talk to me about it or discuss in other books. There is also Eber-Small model that we did not cover. It is more like understanding the IV relation with respect to a model that we have, which also we have not covered, but you are free to do that as a self study reading, but we are always welcome to email me for any questions. So, with that we will conclude the topics of BJT, and in the next class we will take up the topics of other things like either compound semiconductor or silicon MOSFET, and we will go from there. Okay, thank you.